In section 6.3, we're going to be looking at what's called the central limit theorem. A few terms we need to know first. Sampling distribution of sample means. It's exactly a distribution of what it says it is. Distribution of the means computed from all possible random samples. So it's computed using all possible random samples of a certain size taken from a population. So all possible random samples of the same size are taken from the population. That's how you get that distribution. Sampling error, it's just the difference between the sample measure and the corresponding population measure, just simply because your sample is not going to always be a perfect representation of your population. So there will be some sampling error there. So population mean versus sample mean, there's going to be a difference between those because the sample isn't going to always perfectly represent your population. So when all possible samples of a specific size are selected, here's a key word for you guys. With replacement. So when all possible samples of a specific size are selected with replacement from a population, the distribution will have two specific properties. The mean of the samples will be the same as the mean of the population. The standard deviation will be equal to the population standard deviation, but we have to divide by the square root of the sample size. That's going to be the difference between those. Standard deviation of the sample means is also called the standard error of the mean. Just one little notation. I know some of you are like, oh, what did this part mean? This is really your X bar, and that, remember, is denoting your sample mean. That is denoting your sample mean. That's what the X bar means. Just a little reminder for you there on the notation. So the central limit theorem, big idea of our section. As your sample size increases, remember that little lowercase n represents our sample size. As it increases without limit, the shape of the distribution of your sample means is going to approach the normal distribution. The distribution that results will have a mean, and remember the mu is our mean, and a standard deviation. We have our standard deviation of our population divided by the square root of our sample size. So when you're using the central limit theorem to answer questions about sample means, we do have a new z-value formula. There it is. So if you need some of the pieces, you have your X bar is your sample mean. Your mu is your population mean. The lowercase sigma, that's your population standard deviation. And then that lowercase n is your sample size. So just the n, not the square root of n being your sample size, just the n is your sample size. So that's our new z-value formula. And again, we're looking at a distribution of sample means. So it's not just a distribution. I know we've been working with the normal distribution and we've been looking at just some specific data values. Now we're looking at sample means. So when the original variable is normally distributed, the distribution of sample means will also be normally distributed. So if you have that key phrase that we've been looking at, saying that the variable is normally distributed or approximately normally distributed, if your variable's that way, then your distribution of sample means will also be the same way. When the distribution of the original variable might not be normal, so if you don't have that key phrase that the variable is normally distributed or approximately normally distributed, you have to have a sample size of 30 or more if you're going to use the normal distribution while using your sample means. Okay, so those are our three questions for our central limit theorem, or our three properties, excuse me, that we have to use our central limit theorem. So just a couple examples when using this. If you look at number 12 on page 352. All right, so question number 12 says, we're looking at teachers' salaries in North Dakota. The average teacher's salary in North Dakota is $37,764. Assume a normal distribution with a standard deviation of $5,100. So there's that key phrase for us that tells us we can use the normal distribution not only just for a single data value, but also for dealing with sample means. Okay? All right, so letter A asks us, what's the probability that a randomly selected teacher's salary is greater than $45,000? So in letter A, we just want just the $45,000 for one specific teacher. I'm not looking at a mean right now. So I know some of you are thinking, oh, let's just jump right into using that new z-value formula. It says nothing about the mean of the salary being $45,000. Doesn't say anything about selecting a sample. So letter A is not dealing with sample means. Letter A, I don't jump in and say, hey, central limit theorem, here I come, because that's what the section we are doing, that's the title of it. You have to think about, is it going to be what we previously worked with, or is it going to be the new idea? So this is just one single data value of $45,000, and we want to know if it's going to be greater than it. So this one is just plain old, the z formula we've been using with our standard normal distribution. Take our data value, $45,000, minus our mean, which was $37,764, divided by the standard deviation of 5,100. So if you need to use the new formula, and we'll see that in just a minute, there needs to be something in there about a sample and the mean of the sample. If it just wants to know if we're going to have a salary greater than $45,000, there's no mention of a sample, there's no mention of a mean. I just want to know for $45,000, a single data value. That's what we've been doing. That's what we've been doing. So let's draw our picture. We want greater than $45,000. So let's see, we do this, z comes out to be roughly 1.42. And again, just go to the nearest hundredth. I know we talked about that earlier with the z-values. Just round to the nearest hundredth. Then table people and calculator people will all be on the same page. 1.42 somewhere over here off to the right. And we want to know if the salary is greater than, so we're going to shade the area off to the right. So same as we've been doing, you can either look up z is 1.42 in table E, or you can use your calculator. It doesn't matter, however you want to find that area. That area should come out to be 0.0778. And if you're just asked for what is the probability, I know we've been working on the application piece with this quite a bit. If you're just asked what is the probability, it's totally fine if you want to leave it as a decimal. If you feel moved to turn that into a percent, that's fine as well. Totally up to you. Either way's fine. Now, letter B. Letter B says, for a sample of 75 teachers, what's the probability that the sample mean is greater than $38,000? So now letter B is talking about a sample of 75 teachers, and it wants to know the probability of something dealing with a sample mean. So there's how you know, Miss Golly, what's the difference between what we're doing in letter A, which is what we've been working on, and the new stuff, which is what letter B is focusing on. Letter A, the stuff we've been working on, single data value. No mention of taking a sample, no mention of sample means. Letter B now talks about taking a sample of 75 teachers and wants the probability that the sample mean. There's your keys to what we need to do with our new Z formula, or when we need to use our new Z formula. So when you're talking about a sample and sample means, now we have to use our new Z formula, where we take the sample mean, which we're looking at $38,000 as our sample mean, minus our population mean, divided by standard deviation, divided by the square root of the sample size, which in this case they tell us we want a sample of 75 teachers. So again, how do I know when do I use what we did in A versus what we did in B? Letter A made no mention of taking a sample, made no mention of sample means. It just wanted to know the probability that the salary is going to be greater than $45,000. Just a single data value of $45,000. Letter B though, letter B mentions taking a sample of teachers and it mentions a sample mean. That's how you know we need to use this new Z formula before we can find our probability. That's how you know the difference. Now the computation piece, guys, take a little pause here and try out the computation. Make sure that you can get your Z value to be 0.4. So now that we have our Z value, let's draw our picture. Z is 0.40. And we want to know the probability that the sample mean is greater than that. So either look up your Z value in table E or use your calculator, whichever you've come to like at this point. The area there should come out to be 0.3446. Again, we're just asked for a probability, so the decimal is absolutely fine. I know for some of you, probability, you think in your brain it has to be a percent. It doesn't matter. I'll take either answer when asked for probability. If it specifically asks you for a percent, I will expect percent. But if it just says probability, either way's fine with me. Either way's fine. I want to give you guys a chance to try one. Number 22, just on the page right next to it. Just look at A and B. That's all we need to focus on, A and B. I'm going to write the solutions up here, and I want to give you guys a chance to try them. The final topic that we need to discuss with the central limit theorem is called the finite population correction factor. Here's when this comes into play. It's this big, ugly formula. It is. And you don't have to use it very often. Here's when you have to use this. Your samples are drawn without replacement. That's the first indicator that you're going to have to use this to find your standard deviation. Holy cow. But it doesn't happen often. It's just when samples are drawn without replacement, or when the sample constitutes at least 5% of the population. So we have without replacement, your sample constitutes at least 5% of the population. And your population is also finite. So it doesn't happen often. I'm not going to ask you guys to do this often. I just want you to be aware of it. So samples drawn without replacement from a finite population, or if your sample constitutes at least 5% of the population, then you're going to want to use this. Okay? So then if you want the whole formula for Z, this, folks, is just for the standard deviation. That's just for the standard deviation. So if you want the entire Z formula, that's what it becomes in the bottom right corner. So that's what you would then use. So let's try this one out. Let's look at number 26. Now, the directions above question 26 say to check to see whether the correction factor should be used. If so, be sure to include it in the calculations. Now, if you're thinking, Miss Gala, yeah, I don't know if I'm really going to be able to pick out when to use it. For our purposes, guys, if I ask you to do something like this on the test, I would give you directions just like you see above 26 in your book. Okay? I'm not expecting you to be that good that you're going to pick out those things. So I will ask you, check to see if the correction factor should be used. I will ask you to check that, and if it should be used, I will ask you to use it. I will give you that little cue, just like there are other directions in your book. So in 26, we have a study of the life expectancy of 500 people in a certain geographic region. The mean age at death was 72 years. The standard deviation was 5.3 years. If a sample of 50 people from this region is selected, find the probability that the mean life expectancy will be less than 70 years. So let's write down the information that we know. Capital N is your population size. And it says we have 500 people. The sample that we're going to take of those 500 people is 50. The mean life expectancy was 72. You can put the 0.0 if you like. Your book has 72.0. Standard deviation was 5.3. So how do we know if this correction factor should be used or not? It doesn't say anything about sampling being done with or without replacement, so that's not going to help us out much. So we need to check the second piece of that. Does our sample account for at least 5% of our population? So our sample size is 50. Is that greater than or equal to 5% of our population? 5% of 500 is 25. So we'll just make a little note here. Sample size accounts for more than 5%. Oop, I need that diagram. Of the population. So the correction factor is used. So if there's no mention about replacement, without replacement, things like that, if there's no mention of that, then that's going to be your cue. If you need to check for if the correction factor should be used, check the 5% rule. Check the 5% rule for your sample size. If your sample size is at least 5% of your population, you're going to use your correction factor. Okay? All right, so let's dig in. We've got a giant Z formula now. So we have our sample mean minus the population mean divided by, now here's where things get a little bit ugly, our standard deviation divided by square root of our sample size times the square root of population size minus sample size divided by the population size minus 1. Remember, when you see the capital N, that is your population size. I know capital N is not a variable we've used very often, but it represents your population size, is your capital N. So our Z value should roughly come out to be negative 2.81. I would like you to please take a little pause here, guys. Take a minute. See if you can get that using your calculator. There's no shortcut for this. There's not going to be any magical calculator program that's going to do this for you. So take a minute and see if you can get that. And if you can, then go ahead and draw your picture and solve from there. After you've come up with your z-value, like I said, guys, go ahead, label your picture. We want less than 70. We like when we have to find areas to the left, table or calculator. They're pretty easy. And again, you're asked for a probability. So you could say 0.0025, or if you want to do a percent, you can. I'll take either if you're being asked for a probability. I only have to have percent if you're being specifically asked for a percent. Okay? So now again, having to use this correction factor, I'll make sure I have something in the directions. If I give you a test question like this, I'll make sure I have somewhere in the directions that says check to see if the finite correction factor should be used. I'll make sure I have something there indicating it. I don't want you to do this for every question. Okay, so I will make sure there's something like that. Otherwise, our big difference today, we have a little bit different z-value formula. We're looking at samples and sample means, not just individual data values. That's the difference between what we've been doing and the new part today.